Let's see what a quarter cycle rotation around the unit circle does to trigonometric functions. We're going to focus specifically on the sine and cosine functions. This video is very closely linked to the previous video in the quantum mechanics playlist. You can find a link in the description below. So make sure you watch that video. We're actually introducing the coordinates that we can use in two-dimensional space. And we're specifically talking about polar coordinates. In the previous video, I introduced the unit vectors for polar coordinates. Those were r hat and theta hat. And we wrote those vectors in terms of other unit vectors. And we wrote them in terms of I hat and j hat. I hat and j hat are the unit vectors for the Cartesian coordinate system in two dimensions. So we were expressing the unit vectors for the polar coordinate system in terms of the unit vectors for the Cartesian coordinate system. And when we did that, we had to use sine and cosine. And particularly, we had to see what happens to sine and cosine when we add pi on 2 radians to the angles. So what happens when theta goes to theta plus pi on 2? And pi on 2 radians is the same as 90 degrees. That's a quarter circle rotation. So let's have a look at this diagram. In this diagram, I have included just the top half of the unit circle. So we're not actually interested in the bottom half of the unit circle. This is just a semicircle that goes above the positive part of the vertical axis. So this over here, this is the horizontal axis, and we're just interested in positive values for the vertical coordinate. So these properties actually work for any angle around the unit circle, but we're just going to focus in on one angle over here, which we're going to define to be theta, and we're going to have 90 degrees plus that angle. So let's have a look at some of the features of this unit circle. This circle over here, every point on this circle satisfies a certain property. Its distance from the origin of the coordinate system has to be equal to 1. That's where the name unit circle comes from. It is unit length away from the origin. So all of these points satisfy that property. Every point that is linked to the origin by this line over here, that line is actually the radius of the circle. So this is the radius of the circle, and this is the radius of the circle. I have defined these two lines to be perpendicular to each other. So what we can do is we can specify that this is actually 90 degrees. This is perpendicular. And what I've also done is I've dropped a line, a vertical line, that goes from the point on the circle down to the horizontal axis. I've done that for both of these points. This point, I'm actually going to describe in a second, and then we're going to move on to this point. But first, we need to have a look at the angles. So I'm going to define the most important angle over here. This angle I'm going to call theta. So theta, if you remember from the previous video, tells us how far above the horizontal positive axis we are. So we start over here. This is theta equal to 0. If we go upwards, that's a positive angle. If we go downwards, that's a negative angle. This definition works all the way around the circle. So what we can do is we can actually take this diagram and we can rotate it around by whatever theta is. So if theta is equal to 0, then this guy lies on the horizontal axis and this guy lies on the vertical axis. Now, what are these lengths going to actually correspond to? I'll give you a little hint as to what they correspond to. This horizontal unit distance from here to here, that corresponds to the unit vector I hat. And this one up here, this corresponds to j hat. So these guys correspond to the Cartesian unit vectors, and we'll discuss that in a bit. These guys correspond to the polar unit vectors. So this one is the unit vector in the radial direction, which is r hat, and this one is the unit vector in the tangential direction, that is theta hat. And those guys depend on the angle theta. So they're not fixed in space. I hat and j hat are fixed. They're not changing. But these guys, r hat and theta hat, they're going to be changing. They depend on this angle theta. Let's have a look at all the other angles in this diagram. So this triangle over here has theta over here, and it has pi on 2 radians, or 90 degrees in this corner. This is perpendicular. So from that, we can actually conclude that this angle has to satisfy a relationship. All of the angles in a triangle on a flat plane have to satisfy this relationship. They have to add up to 180 degrees, which is pi radians. So what does this angle have to be? If we add theta to pi on 2, what do we have to add to make this equal to 180 degrees? Well, it turns out what we have to add is pi on 2 minus theta. That's what we have to add. So this is actually pi on 2 minus theta. Let's see, does that actually work? If we have theta and we add to that pi on 2 minus theta, this minus theta and this theta are going to cancel each other out. So we'll just be left with pi on 2, and this is pi on 2. Pi on 2 plus pi on 2, that's pi. So we have a half plus a half, and that's a whole. So what we have is this is actually satisfied. So these guys will add up to 180 degrees, which is pi radians. So what is this length over here? This length is 1. Why is it 1? Well, it's the radius of a unit circle. So it has to be 1 by definition. What about this side over here? This length is also 1. We have 1 over here. What about this angle? The angle that goes all the way up to here. So from here all the way to this line over here. This guy is perpendicular, so these guys have 90 degrees, and this guy is theta. So what we have to do is just add those two angles. So this total angle over here, that is equal to pi on 2 plus theta. So over here we have pi on 2 minus theta, and over here we have pi on 2 plus theta. So you can see, we have to be very clear, this is theta, this little guy is theta. All of this from the horizontal positive axis, all of this stuff, all the way up to here, that is pi on 2 plus theta, because we're adding theta and this 90 degrees over here. So I keep using 90 degrees and pi on 2 interchangeably. That's because I want you to get used to switching between radians and degrees very quickly, because this is very important. Radians are a far more natural unit to work with, and that's why physics and engineering tends to use radians a lot more than degrees. Degrees are a kind of an arbitrary way of splitting up the circle into 360 little chunks. So that's why we're focusing on radians. Now let's have a look at this triangle over here. What's going on with this triangle? Again, we see a right angled triangle, but what are these two angles? Well, one thing that's very, very peculiar is that the proportions are actually the same. This horizontal distance is the same as this vertical distance, and this vertical distance is the same as this horizontal distance. So what's going on over here? This is the same as taking this triangle and then flipping it on its side. We make sure that the hypotenuse is still over here. We still have the radius equal to 1, but these sides have been swapped. So that means the angles have also been swapped. This guy over here has to be theta. So then we have theta over here. And what about this guy over here? What is that equal to? Well, this, because the angles have been swapped, has to be equivalent to this guy. So we have pi on 2 minus theta. And again, if we add these guys, we're going to get pi radians, so 180 degrees. This theta and this theta cancel, and we're just left with pi on 2 plus pi on 2, which is pi. So both of these guys are satisfying all the rules that they need to be satisfying. So they've satisfied the property that this point lies on the unit circle, so it's unit length, and they've also satisfied the property that all the angles in a triangle on a flat plane have to add up to 180 degrees. Now notice how I'm saying on a flat plane. This may not be true in general, but it works for Euclidean geometry. And what we're dealing with is Euclidean geometry. This is a flat space over here. This is very flat. The whiteboard is a flat space. So now we have all the angles that we need. Let's talk about some of the lengths. So what are the distances over here? If you take this point over here and you imagine a light source directly above this line over here. So imagine this is like a vector in 2 dimensions. And what we're doing is we're taking the projection of this vector down onto the horizontal axis. What is that going to be? Well, it's going to be the shadow that this guy casts down. And that's actually equivalent to cosine of the angle. So this length over here is cosine of the angle. And what I'm going to do is I'm going to write that over here, because that is actually the same length as this side over here. This is cosine of the angle theta. So this is the same length as this guy over here. We've just lifted that triangle up and we've swapped its sides and its angles. What about this length over here? That's what would happen if we had a light source over here and we cast a shadow of this vector onto the vertical axis. What would that be? Well, that has to be sine of theta. So I'll write sine of theta over here. So we have sine of theta. And sine of theta is the shadow that you get onto the vertical axis. So this is actually a way of writing the components of the vector. This is cosine theta and this is sine of theta. So what are the coordinates of this point? Well, this point has some very interesting coordinates. I'm going to write the coordinates over here. The x coordinate is cosine theta and the y coordinate is sine theta. So we have cosine theta and then we have sine theta. So the horizontal component is given by cosine theta, and the vertical component is given by sine theta. What about this guy over here? What are the coordinates of this guy? Well, what we have is cosine of theta is the vertical component now, and the horizontal component, what is that? Well, what I have to add over here is not just sine theta. It is the same length. The magnitude of the length is the same. But the problem is, these guys are both in the positive direction. This is the top right quadrant, where both x and y are positive. But now over here, we're in this quadrant. And this quadrant has the vertical component is still positive, but the component in this direction, the horizontal component, is negative because it's towards the left. And the left is defined to be negative. So this is no longer sine theta. This is minus sine theta. So this is a very important point. This is no longer sine theta, it's minus sine theta. So now let's write the coordinates. Minus sine theta is the horizontal coordinate, or the x component of this vector. If we imagine this as a vector, this is minus sine theta. And this distance up here, that is cosine theta. So what I'm doing is I'm packaging these guys up as Cartesian coordinates. This is the x distance, and this is the y distance. So can you see what happened over here? We rotated a quarter of a cycle around the unit circle, and cosine theta went to minus sine theta. And what did sine theta go to? Sine theta went to cosine theta. Now, if you've done calculus before, you will recognize these relationships. This is differentiation. The derivative of cosine is minus sine, and the derivative of sine is cosine. So these guys are linked to differentiation. And differentiation is actually linked to rotating a quarter of a cycle. So rotating pi on 2 radians, or adding pi on 2 radians to the angle. And that is linked to this process of differentiation. So calculus actually comes into this. That's a very important and deep relationship between trigonometric functions. So the most important diagram when dealing with trigonometric functions is actually the unit circle. Now, why can't we just generalize and have some other length instead of 1 over here? Well, the thing is, the unit circle covers every possible case, because what you can do is you can just scale all of the lengths proportionally, and you will get any length. So that's why we don't have to put any radial distance. We don't have to have r cosine theta and r sine theta, because r is equal to 1. And if we wanted to extend this to a circle that's bigger or smaller, we would just multiply by a factor of r. So that is the powerful nature of this diagram. This diagram is very, very powerful. You can derive a lot of relationships between them, between the quantities and the lengths and the angles over here. So what is another thing that I want to stress? I want to show you that this circle actually can be used to derive a number of trigonometric identities. And the one that we're going to focus on in this video is one that we've actually used in a few of the other videos, and that is sine squared theta plus cosine squared theta is equal to 1. So how do we get that? Well, we know that the circle has to satisfy x squared plus y squared equals 1. You can think of this implicitly as 1 squared, because you're taking the square of the radial distance. So in general, for any circle, this is r squared, or the radius squared. So every point on the unit circle, even the point in the semicircle that's not shown over here, the one below, where the vertical component is negative, they all have to satisfy x squared plus y squared. If x squared plus y squared is less than 1, then you're inside the circle. But if x squared plus y squared is greater than 1, then you're outside the circle, you're over here. All of the lines where this is equivalent, where 1 is equal to x squared plus y squared, those are the points that sit on this unit circle. So it's actually a line that it's a line that gets traced around, and that is what a circle is. The circle has to satisfy this relationship. So all the points of the circle have to satisfy that. Now, because we know what x and y are for this coordinate over here, we can substitute them in. We can see that cosine squared of theta plus sine squared of theta, that has to be equal to 1. This is the x component, and this is the y component of this vector over here. So what about this side over here? Why can't we just square these guys and get this exact same result? Well, we actually can. If you take the square of this, the minus sign disappears, and these guys just get swapped around. But keep in mind that this theta is not the same theta in this little triangle over here. This theta is used explicitly for this triangle. And we're extending that theta and we're using it, we're borrowing it for this triangle as well, because this triangle shares some properties with this triangle. Namely, it's just a swapped over triangle where the lines, the side lengths are actually swapped and the angles are swapped. So what is the most important message of this video? We're actually trying to get that relationship that we talked about in the previous video, the one between r hat and theta hat and I hat and j hat. So that relationship, I'm going to write that down, and now you're going to see visually a little proof as to why that actually works. So let's write down r hat first. R hat, if you remember from the previous video, is equal to cosine theta times I hat, and it's equal to sine theta plus, or sine theta j hat. So this is the definition of r hat. So we're writing r hat in terms of I hat and j hat. And where are these guys in this diagram? Well, this over here, this guy, if we draw an arrow up to here, this entire vector quantity, that is actually I hat. So that's what I was stressing on before. This is I hat. And this, if we draw a line over here, this vector quantity from the origin up to here, that is equal to j hat. What about this guy? Well, this guy is equal to, I'll draw a little arrow over here, this guy is equal to r. Ooh, that's a bit of a ugly r. R hat. So we've got r hat over here. And that is the unit vector in the radial direction. What about this guy over here? This guy is theta hat. So don't confuse this with theta. The angle theta doesn't have a hat on it, but the unit vector has a little hat on it. And it's a special type of vector. That's because we put a little hat and we say that is a unit vector that we're going to use to construct all the other vectors. So this guy is pointing in the tangential direction. I'll add a little arrow over here to signify that it is a vector quantity. So these are the four vectors that we described in the previous video. Now let's write theta hat in terms of I hat and j hat. So theta hat is equal to, what happens when you rotate a quarter cycle around? Cosine turns to minus sine. So now we have an explanation as to where that minus sine theta came from. So we have minus sine theta, hence I hat, and then we have to add to that cosine of theta times j hat. So have a look at what happened. What we did is we broke up r hat into its horizontal and its vertical component. And those depend on theta. They're related by trigonometric functions, and those are cosine and sine. So that is a pretty simple part of the relationship. But the more complicated part of the relationship is this part over here. How do we get minus sine theta and cosine theta? Well, now you can see from this diagram, it emerges visually. You can see that all you have to do is you have to take this triangle, lift it up, flip up the sides, and then swap the angles. And what do you actually see? When you swap the angles, you also swap the sides. So then you get this triangle. And this triangle has a horizontal component that is minus sine theta and a vertical component that is cosine theta. This combination shows up a lot. Anytime you have any sort of rotation in 2 dimensions, you'll have this sort of relationship. If you've done linear algebra before, you might recognize these guys as the components of a rotation matrix. These guys actually take the unit vectors to their new rotated counterparts. So these guys, r hat and theta hat, are the unit vectors, but just rotated. And so anytime we have this angle specified, we can find these 2 guys. So all we need to know is the angle, and we can find these guys with no problem. So are these guys dependent on time? Well, they could be. If the angle changes with respect to time, then these guys change with respect to time. So this is a coordinate system that moves with the particle. And if the particle is whizzing around some sort of center of rotation, then these guys are a very appropriate choice, and they're very convenient coordinates to work with. These guys are very convenient if you're just interested in keeping your coordinates fixed. So I hat and j hat are these guys, the horizontal and vertical unit vectors for Cartesian coordinates, and these guys are the unit vectors for polar coordinates. Hopefully this video has helped you see a geometric, a visual intuition as to what is going on with these guys, with this relationship. Why is there a minus sign there, and why does cosine and sine get swapped when you rotate a quarter of the cycle around the unit circle? Now you can see this, and I want you to actually draw this diagram and try and play around with the lengths. I want you to see if you can start off with defining some things and then deducing other facts from that. So use properties that you know. You know definitions. You know definitions like this. Every point on the unit circle has to satisfy x squared plus y squared equals 1. And you also know that every triangle has to have all the angles add up to 90 degrees. And then you also know some basic trigonometry from right angle triangles. So right angle triangles are very convenient when it comes to trigonometry. So you have all of these basic facts. You have the toolkit that you need to construct all of this stuff by yourself. So that's what I want you to do. I want you to draw this diagram by yourself and deduce some relationships based on the definitions that you know. So I hope this video was useful, and now you see where these two relationships come from. In the next few videos, we're going to be using polar coordinates, and we're going to be examining some of the relationships between things like position, velocity, and acceleration in polar coordinates. Why are we doing this? Well, this is all going to be very useful in classical mechanics and in quantum mechanics. That's why this is in the quantum mechanics playlist. This is all precursor knowledge for quantum mechanics. So if you want to find those other videos in the quantum mechanics playlist, you can find them if you click over here.